2H plus and 2 electrons. It can go this way or that way. And if it's above, then it goes this way and the hydrogen goes this way. Okay, you will see this, get a hang of this soon. So this potential we call zero, and we measure everything relative against that potential. And the standard hydrogen electrode is you have a glass tube here, that's a glass tube, and you blow hydrogen gas into that glass tube at 1 atmosphere. That hydrogen gas has 1 atmosphere partial pressure, and you blow it into a solution that has a hydrogen ion concentration of 1 mole. Okay, now this can happen or that can happen. Depends. If this happens, then it is one sign. If that happens, then it's the other sign. Because you don't have, hydrogen is not a metal, you need to somehow transfer these electrons. So you put a platinum wire there and a piece of platinum so that reduction and oxidation happens on the surface of the platinum metal, and the platinum will carry the electrons. It will not be involved in the chemistry at all. It will just carry the electrons. Okay, the electrons that are either taken up, it will be taken up by of course, the platinum wire you connect as this one half cell, you connect this to your other half cell, and then either the electrons can flow in here or flow out. Okay, and with this you do your measurements, and this is what we're going to do now. So we measure the first time we measure, we look at the standard hydrogen electrode, and then we measure copper, the copper potential, and the copper potential, okay, which one is the reduction, which one is the oxidation. The copper 2 plus will be oxidized to copper metal, okay? This is obviously the reduction, that's the right side, okay? And the hydrogen, what will happen to the hydrogen at the hydrogen electrode? The hydrogen gas will go to 2H plus and 2 electrons, because this goes this direction, okay? But somewhere the electrons have to come from, so this goes that direction. It's generally the case. If you have the potential, this is called the Latimer standard reduction potential, you write that the higher the potential is, the more of an oxidizer it is, okay? So that means if this here is above that here, this one goes this direction, that one goes that direction. Or this one, if I compare this would go this direction, and this would go that direction, okay? So now let's see, that's how we are, 0.34 volts. Let's do that, Karen. So let me first explain in detail to you the hydrogen electrode. So we have here on the bottom, you see this piece of metal there, the dark metal there, the little piece of excellent, I can't remember, my fingers are even seeing. This piece of dark metal, this is our platinum. It's platinum black, actually has a bigger surface, and it's connected to that wire up here, which is our electrode, okay? And so we flushed in, we flushed in here, through here, 1 atmosphere of hydrogen gas, and this is a solution of 1 molar H2SO4, okay? So it's 1 molar in H plus or in H3O plus. So now Karen gets that electrode ready. This is our reference electrode, and everything you measure, every other half potential you measure against this. Now it's either positive or negative. Positive is it when something oxidized becomes reduced, then it's positive. And negative is it when this goes in this direction, this comes in this direction, when something becomes oxidized. Okay? So let's have a look at this, what that potential is. So far it's 0. We have forgotten something. We need that bridge there, that electrolyte bridge. Let's take a look at that electrolyte bridge. You see that's that agar, it has the potassium nitrate in there. And the moment Karen will close the circuit, you will read here 0.344 volts. And what? Oh my God. No, Karen. It's 0.34 volts. It's absolutely perfect, you know. And this is not a high precision measurement. So that half cell potential, that's what copper with a copper metal inside 1 molar copper solution with a copper metal inside will go in this direction. That means the copper will get reduced to copper metal, and the hydrogen itself will be oxidized to H plus ions. Okay. So that if it's positive, it goes this direction. So first this and then that. And if it's negative, let's see what we can do if we put in zinc sulfate instead of copper. What should we read there? What should you read there? Minus or plus? Minus 0.76. You are great. Okay. Now let's do that. Yeah, we're a little low, but it's not a high precision measurement. We have minus 0.7172 volts. Okay, we're a little bit off. You know, the concentration is not 100% 1 molar, or if it's not 1 atmosphere exactly. So there's all kinds of things that. So you see, that's minus. So this goes in this direction. The hydrogen ions get reduced to hydrogen gas, and so somebody needs to furnish these electrons. The zinc goes into solution, produces these electrons, and they are taken up by this. So it goes this and that. So if you are above, the one above always becomes reduced. Okay, and it oxidizes the one below, right? The oxidation reaction is this here. The one above becomes reduced, and it oxidizes the one below. The one above becomes reduced, and it oxidizes the one below. Okay, you go in the opposite direction then. So I want to show you one more thing. The salt bridge, you can do away with the salt bridge if you are a human being, and I just take my 2 fingers, okay? This is my salt bridge. Now what happens? You think it's going to work? Let's try that. Are you ready? You have the voltage. So now let me get in here. Can you read anything? 1.0. I'm on with my arms in the. There it is. 1.03 volts, huh? Isn't that something? We are nothing but a bag of salted water. So there's positive ions and negative ions providing the electron neutrality, and with this the circuit is closed. And so I could use all of you, and you wet your hands, and you all hold hands, and one puts it here, put the finger in here, and the other one put the other finger in there, and the whole chain is you, and that would read the voltage. Of course, you have an IR drop because we all have resistance, so the voltage will not be that high. And if I have too many, I don't read anything anymore. But with about 20 people, I have done this, and I read the voltage. Okay? Thank you. All right. Thank you, Karen. That was excellent. So you now have seen a galvanic cell that it produces electricity just from chemical reactions. And the other thing is that we have a Latimer, that's what this whole is named after, a standard potential table, the standard reduction potential. Latimer did it in the opposite way. They changed the convention in the 70s or late 60s. Latimer called them oxidation potential, had everything written in the opposite direction. Okay, but we call it reduction potential now. The IUPAC has decided that, and we went along with this. So this was this one here. So the zinc goes into the solution, isn't that right? The zinc went into the solution, yes, provided the electrons for the hydrogen ions to become hydrogen. So which one is my red cat here? Where's the reduction in this one? Where's the reduction? On the left or on the right? Is that the oxidation? The zinc goes in solution, is that right? Provides electrons, so that's the oxidation. That's my reduction is this here. The reduction is the hydrogen picks up these electrons, becomes H2. Okay, that's the red cat here. It should be written on the right side actually. Right? We always write it on the right side, the reduction. Okay, let's see where we are now here. There are many potentials being listed, and these are half cell potentials against standard hydrogen. This will always be 0, and if you're above here, this goes this way, and anything below goes this way. Okay, so copper would be reduced when it's in combination with zinc, and the zinc would be oxidized. That's exactly what we have seen, isn't that right? And so because this is negative against the hydrogen here, and this is positive against the hydrogen, goes this way and that way, and this goes this way and that way. All right? So let's see if you understand. And I'm not so sure if this is all clear to you, and it's a difficult subject, but this is also a bit of a difficult question, as I'm known for. When we have copper, copper is placed in sulfuric acid. So there's H plus here, or HVO plus, 1 molar, and I put copper in there. Would the copper dissolve to copper 2 plus ions? Would hydrogen be generated, or nothing at all would happen? I have copper metal right there in sulfuric acid. What would happen? So now you need to look at this table and think very hard. Don't go with the obvious, okay? Think very hard. I have copper metal, all right? So why don't you give it a stab and try if you get an answer for that? It's difficult, but at least by next lecture you will have it all down pat. The question is, will the copper dissolve? Will hydrogen be generated, or nothing happens? I have this in copper sulfate solution here. No, I have it in, not sulfate. I have copper metal in sulfuric acid, and that means H2 and H3O plus or H plus. This equilibrium you have here. See, we are sloppy now. We don't write the H3O plus anymore. Okay, that's a good number. And it's 26, 38, 36. 26, 38, 36. Yeah, that's pretty good for the beginning. Don't discourage. Just think a little bit more about this. What do I have in solution? Do I have this in solution, or do I have this in solution? Okay, so think about it and discuss it with each other, and then I will give you the answer. What is it? What is it? Absolutely. Huh? I need to start it too, huh? All these details. So what is it? Yeah. Oh, that's not so bad. It could be worse. Actually, it's pretty good for now because it's a very foreign concept to some of you. And so we have already copper, okay? We don't. You see anywhere copper ions in here? No. You have copper and you have hydrogen, okay? You don't have any hydrogen gas either, all right? So if you you probably fell into that trap here. The trap that this is 0.34 volt, but I don't like that here. That exponent. Yeah, let's go this way. I like it more. Have a look here. We have that copper here. That's already copper 2 plus, but you didn't have any copper 2 plus in there, so this is not going to happen. All you had is copper. That's that copper here, and then you had H plus ions. H plus ions, copper. So where did the copper? You see any copper picking up, giving off electrons here? No, that's the oxidizer. It will never. If this is the most positive, it will never go in this direction. It will all the oxidizer will always go in this direction. Anything below can go in this direction. But with this one, nothing happens because you had that already. So this is how you write this reaction, and so this didn't happen at all. There were no electrons at all that could be given to make copper 2 plus. Okay. So let me ask you another one. And we just need these tables here. We have zinc. We're putting zinc metal into sulfuric acid. Zinc metal into sulfuric acid. What will happen? A, B, or C? Why don't you give me your answer? Now you will get the hang of it. Or in English, you will understand better. So you have a zinc piece of zinc in your solution, and you have H2SO4, so H plus, and SO4 to HSO4 minus, or H2 in 1 molar. Okay? A, B, or C? Somebody. Okay. Oh. Okay. So you have. So which one is the oxidizer? This one here. And which one is getting reduced then? Which one is the oxidizer? That's the first question. And what will happen if you have an oxidizer? You also need a reducer. Yeah. The reducer gets oxidized. The oxidizer gets reduced. All right. Why don't you discuss this with each other and get a little bit more confused? I'm just kidding, actually. Come on, discuss it. It's very important. Let's have some fun with this. So which direction will these reactions go? You have them all written there. You have them. Oh, my. Okay. Now we're going all in different directions here. Huh, let's just see. So, okay, obviously the sink goes into solution. Aha! A and B it was. Of course, the hydrogen here goes this way. It's the oxidizer that gets reduced. The H plus gets reduced to H2, to hydrogen. And so it picks up 2 electrons. Where does the electrons come from? It comes from the reducer that gets oxidized. That's the reducer. It gets oxidized to zinc 2 plus. And with this, you have the generation of hydrogen and the creation of zinc 2 plus. And I'm very proud of you, by the way. Okay? Alrighty, good. See, it's not that difficult. We talk about this the next time in more detail.